Hello, my name is Shahriari, and this is a lecture in a series of lectures on undergraduate abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. This is a part of the ring theory section of our lectures, and this particular lecture is about Zorn's lemma, about Kuratowski-Zorn's lemma, the basis for vector spaces, maximal ideals in rings, and spanning trees. So let's get started. So here are the motivating questions, the questions that we want to sort of answer in some sense. Does every vector space have a basis? Is every ideal of a ring contained in a maximal ideal? Or does every connected graph have a spanning tree? This is a question in graph theory. All of the answers to all of these questions is clearly yes, if the objects that we're studying are finite ones, like if it's or a finite dimensional vector space, or a finite ring, or a finite graph. And some of you might only be interested in those. In fact, I'm one of those people, and in which case these questions in this generality maybe are not as significant. But if you are interested in general, then the problem is that these questions cannot be answered in general using the basic axioms of set theory. Mathematics is based on set theory, the study of sets, and there's a set of axioms called the Zermelo-Fraenkel axioms that have over time been introduced as the ones where mathematics is based on, and all of those seem sort of reasonable, uncontroversial axioms. And the point is that using ZF, using these axioms, we can't answer these questions. And it's not that we can't answer them because we can't come up with proof, or that maybe we're short an axiom. The point is that each one of these statements, either their truth or their falsehood, is independent and consistent with the current axioms. And therefore, each of them could be taken as an axiom, or their negation could be taken as an axiom. And you would have a consistent mathematics that you could build upon. And so that's what we want to explore a little bit in this lecture. So what's the plan for this lecture? I will need to tell you about partially ordered sets. And because that's what I need to be able to tell you what Zorn's lemma or what Kuratowski-Zorn's lemma is. So then I will tell you what that is. And I will also tell you what the axiom of choice is. And then to be able to discuss those statements, we will remind you what a basis for vector space is, what is a maximal ideal of a ring, and what a spanning tree of a graph is. And we will prove that using the Zorn's lemma that every vector space has a basis, every ideal of a non-trivial ring is contained in a maximal ideal, and every connected graph has a spanning tree. We will then end by talking about the well-ordering theorem and presenting you with equivalent forms of the axiom of choice and the fascinating Banach-Tarski paradox. So let's get started. So what's an ordered set? So the integers are totally ordered. -2 is less than -1, -1 is less than 0, and so forth. You can think of them as sitting on this vertical line, and they're ordered. You know which one is smaller than which one is bigger than another one. As are the real numbers. You could actually think of this straight line and think that you have placed real numbers in here as well. So real numbers are a totally ordered set. The formal definition in just a second. On the other hand, if you look at subsets of 1, 2, 3, so 1, 2, 3 is a set with 3 elements, you can look off all of its subsets and order them by inclusion, meaning that you can think of something less than or equal to something else if it's included, if it's a subset of that. If you do that, then you get a partially ordered set. So in this case, not all sets are comparable. 1, 3, and 2, 3, neither one is a subset of the other one. 1, 3, and 2, 3 are incomparable. You can't say this one is bigger than that one or less than that one in this order being inclusion. Similarly, if you look at divisors of 24, so what I have here, 1, 2, 3, 4, 6, 12, 8, and 24 are all the integer divisors of the integer 24, and I've ordered them by divisibility. So 3 divides 6. It also divides 12 and 24, but it does not divide 4. It does not divide 8, but 4 doesn't divide 3 either. Divisibility is a partial order. Some things are divisible by others, but if you take 2 of these divisors of 24, they're not necessarily going to be comparable. It could be that you pick 2, like 4 and 6. 4 is not a factor of 6, and 6 is not a factor of 4. Okay, a totally ordered subset of a partially ordered set is called a chain. So, for example, here, divisors of 24 is a partially ordered set. And if we look at 1, 2, 6, 12, and 24. If you just limit ourselves to those guys, 1, 2, 6, 12, and 24, then we have a totally ordered set. Within those elements, every two of them are comparable. Every two of them that you pick, every pair that you pick, one of them divides the other. That's called a chain in that partially ordered set. So now for formal definitions, if you have a set and you say squiggle is a relation on the elements, a relation is really a subset of P cross P, but all that means is that you can say that this element is related to that element or not. A is related to B or not. And so A squiggle B means A is related to B. Now this relation is called a partial order if for all elements in that set P, we have reflexivity, X is related to X. We also have transitivity, if X is related to Y and Y is related to Z, then X should be related to Z. We also have anti-symmetricity. If X is related to Y and Y is related to X, that can only happen if X equals Y. Basically, we're saying that you can't have X related to Y and Y related to X at the same time, or you could have that if it's the trivial thing that X and Y are the same. Other than that, you can't have it. If the squiggle is a partial order, it's not just that any relation is a partial order, we usually use less than or equal to instead of it. When we use less than or equal to, we don't mean the usual less than or equal to of numbers, because the elements of P may not be numbers. We have to say what the relationship is, but less than or equal to is our symbol that we use for partial orders. And again, a set P with a partial order is called a partially ordered set or a poset. Now, if every two elements of this partially ordered set are comparable, that means that if you take any pair, you can say this guy is related to that, or that's related to this. This is less than or equal to that, or that's less than or equal to that. If that's the case, then it's not a partial order, it's a total order. And a totally ordered subset of a poset, as I had mentioned before, is called a chain. So we're ready to talk about the Kuratowski-Zorn Lemma, but before we start, I need one more definition. So let P with less than or equal as its relation be a partially ordered set. An element of this partially ordered set is called the maximal element if there isn't anything else bigger than it. So if there does not exist a Y in P that M is less than Y, which means that M is less than or equal to Y, but M and Y are not the same. So maximal element is something at the top of your partially ordered set, something that there's nothing above it. Okay, it doesn't necessarily have to be bigger than everything. It just has to be that there's nothing above it. So what does the Kuratowski-Zorn Lemma that most people know as just Zorn's Lemma tell us? It tells us that if you start with a non-empty partially ordered set, and if you have the following condition, this condition has to be satisfied, is that if every chain in P has an upper bound. So what does that mean? So you have a chain, a totally ordered subset of your partially ordered set. If that has an upper bound, that means that is there some other element of P that's greater or equal to every element in your chain? That upper bound does not have to be a part of your chain. It just has to be a part of the poset. But this condition has to be satisfied, and then Zorn's Lemma tells us that if this condition for your partially ordered set is satisfied, then P will have at least one maximal element. Okay, now sometimes this condition is not satisfied. Like, for example, if you take the integers with the usual less than or equal to, then there is a chain that does not have an upper bound, namely the whole set of integers. There's no integer that's greater or equal to every integer. But Zorn's Lemma doesn't apply there because the hypothesis is not satisfied and the integers do not have a maximal element. Now, we call this the Zorn's Lemma, so it sounds like something that we can prove, and we can prove it, but we need the axiom of choice. And in other words, and in fact, axiom of choice and Zorn's Lemma are equivalent, meaning that if you know Zorn's Lemma, you can prove axiom of choice. If you know axiom of choice, you can prove Zorn's Lemma. But what I mean by new is that these are actually axioms, both of them, equivalent axioms. We have the usual set theory axioms, Zermelo-Fraenkel axioms, and these guys are independent of those. And you have to accept one of them as an axiom, and then you can prove the other one. In fact, you could take Zorn's Lemma to be an axiom if you like. Now, this lemma was proved meaning using axiom of choice, by Kuratowski in 1922 and by Zorn in 1935. And in fact, there's a earlier version that's quite related, is not quite equivalent, but due to Hausdorff in 1914. Okay, now what is this axiom of choice? Axiom of choice says the following thing. It says that if you have a collection of non-empty sets, and in fact, it's relevant only if the set is really infinite. There's a lot of, this collection has lots of the sets in it. So you have a whole bunch of sets. And the axiom of choice gives you it tells you there's something you can do. You can construct a new non-empty set by arbitrarily choosing one element from each of the original sets. So you have all these sets already, and you're going to make one other set. And what are the elements of this new set? They're arbitrarily chosen elements, one from each of the other sets. Now, this again seems very reasonable. It's like, why wouldn't you be able to do that? In fact, if the number of sets you have is finite, then you can actually prove axiom of choice using induction. But the point is that if you have infinite number of collection of sets, maybe an uncountable number of collection of sets, then this is not something that you can prove from the other axioms. And in fact, this is equivalent to Zorn's lemma. So accepting axiom of choice as an axiom, you can prove Zorn's lemma. If you accept Zorn's lemma as an axiom, you can prove axiom of choice. And in fact, these two facts, the axiom of choice and Zorn's lemma, which are equivalent to each other, are consistent with and independent of the Zermelo-Fraenkel axiom. So what does that mean? Consistent means that you're not going to be able to use the usual axioms and come up with a counterexample to them. Independent means that you can't prove them using the Zermelo-Fraenkel axioms. So you can neither prove nor disprove either one of these from the usual axioms that we take as the axioms of mathematics. And therefore, you can take axiom of choice and Zorn's lemma, which are the same, as equivalent. They're not the same, but they're equivalent as an axiom. But you could also take not the negation. So you can actually construct two different mathematics, two different construct, two consistent mathematics, one where axiom of choice is true and where axiom of choice is actually not true. If axiom of choice is not true, Zorn's lemma will also not be true. But the fact that these are consistent and independent of the other axiom means that you could take not axiom of choice as an axiom, and be okay, have a mathematics that works and works. It will have different theorems when it comes to the realms where axiom of choice is used, not for example, in terms of finite things, the two mathematics will be the same. But in terms of places where you might want to use axiom of choice, like the examples we are showing here, there will be two different mathematics. Okay, so now let's talk about the substantive parts. Let's talk about vector spaces. Now, I have a whole a whole set of videos, in fact, a full course on linear algebra. If you don't know what a vector space is, this will not going to make much sense to you. Please watch some of those videos. But very briefly, a vector space is a set with a reasonable addition and scalar multiplication. You can add two elements of a vector space and get another element, and you can multiply every element of a vector space by scalar and get another element, and scalars come from a field. The definition is something like this, that you have V and you have these two operations, addition and scalar multiplication, and these sets together, this non-empty set together with these two operations is a vector space over some field F. Field is a place where you can add, you can subtract, you can multiply, and you can divide by non-zero elements. If V together with plus is an abelian group, so that means that it's closed, it's associative, it has an additive identity is zero, and every element has a negative. But it's also abelian. That's another word for saying that it's commutative, that x plus y is y equals to y plus x. Also, the field F, the scalars, act on V nicely by scalar multiplication, like the kinds of things that you would want to be true, like alpha scalar times x plus y should be alpha x plus alpha y, and things like that work. If V is a vector space, then a subset of V is called a basis. If it spans V, that means that by finding linear combinations of B, you can get every element of V, and also if B is linearly independent. If no non-linear combination of them is equal to zero, except for of course, you could cheat and put all the scalars to be zero when you find a linear combination. As long as you use some non-zero scalar, want to use some non-zero scalar, you can't find some linear combination of those elements equal to zero, then you say that set is linearly independent. And a basis is a subset of a vector space that spans the vector space and is linearly independent. Again, watch my videos on spanning, on linear independence, on basis, and so forth, if these things are not clear to you. Another way of saying what a basis is to say it's a maximal linearly independent set in a vector space. It's a linearly independent set that's maximal. What does that mean? That means that if you add any other element to the vector space, it will become linearly dependent. That will need a little proof from what we said before, but it's true. And again, it's in my videos, explained in my videos on linear algebra. Okay, now I'm going to try to prove to you that every vector space has a basis, but I can't really do that. I can only prove that if I assume Zorn's lemma. So if I assume Zorn's lemma, or equivalent the axiom of choice, but Zorn's lemma is the version of axiom of choice that's very useful in proving these kinds of theorems, as we shall see in the three examples that we see. So assuming Zorn's lemma, every vector space has a basis. Now, clearly in linear algebra, you've seen many vector spaces that have bases. And many of those are finite dimensional vector spaces where the basis is a finite number of elements. You even have seen vector spaces that have an infinite basis, like, for example, polynomials, 1x, x squared, x cubed, x to the fourth, going on forever, is an infinite basis for the vector space of polynomials. But there are other vector spaces for which it's really hard to imagine a basis, like, for example, of real valued functions on the real line. That's a vector space, and what would be a set of functions, even an infinite number of functions, such that they would be linearly independent and would span that vector space. And this theorem says that if you assume axiom of choice and its or equivalent Zorn's lemma as an axiom of mathematics, then you can prove that every vector space has a basis. This is not a constructive proof. It doesn't tell you how to find a basis. It just tells you that the basis exists. In fact, this fact, every vector space has a basis, itself could be taken as an axiom of, and it would be equivalent to axiom of choice and Zorn's lemma. So how does the proof go of proving every vector space has a basis if we assume Zorn's lemma? Now, to use Zorn's lemma, you need a partially ordered set. So first of all, we have our vector space over field F. That's the one that we want to find a basis for. And then we pick our poset is going to be all the linearly independent subsets of V. So every element of P is a linearly independent subset of V. There might be infinite number of elements in that linearly independent set, but it's got to be linearly independent. When we say an infinite set is linearly independent, we mean every finite subset of it is linearly independent. So you look at all linearly independent subsets that you could possibly find, and you order them by inclusion. You say that, look, this guy is a subset of that other one. So this is less than or equal to that. So less than or equal to that here is subset inclusion. And now we have to check the condition of Zorn's lemma. Given a chain in P, is there an upper bound for it? And the point is that a chain in P consists of all these linearly independent sets that are nested inside each other. Well, take the union of that nested set. This idea of taking the union will appear in all the proofs that we see today. Take the union, and this union itself will be linearly independent, because how could it not be? If it's not linearly independent, that means that a finite subset of it is linearly dependent. But that finite subset maybe consists of vector v1, v2, and v5. If that's linearly dependent, then v1, v2, and v5 are all going to be in one of these elements of the posets, which were linearly independent sets in that chain. But that chain was all the subsets in that chain were nested. So there is a bigger one. There's three of them. One of them contains v1, one of them contains v2, one of them contains v5. One of those three will be bigger than the other ones, and that one will contain all three. And so those three elements would have to be linearly dependent inside that subset. But that subset was a linearly independent subset, and that's not possible. So if you take the union of all the linearly independent subsets in a chain, you will get a linearly independent subset of the vector space, and that will be an element of P, and it will be an element of P. Maybe it's not in the chain, but it'll be in P, and it'll be an upper bound for the chain. Every subset in your chain is a subset of this element. And then by Zorn's lemma, P will have a maximal element, and a maximally linearly independent set is a basis for V. And now we're done. We now proved that if you accept Zorn's lemma as an axiom, then every vector space will have a basis. Now note that if you accept not axiom of choice as an axiom, then you will have a world where there are vector spaces that do not have bases. And so you can have a mathematics where all vector spaces have bases, or you can have a mathematics where some vector spaces do not have a basis. That is your choice, depending on whether you pick axiom of choice or not. Now about rings and their maximal ideals. So first, let me, what is a ring? A ring is a set with two operations, plus and multiplication. With plus, it's an abelian group. So you have closure, you have associativity, you have additive identity 0, and you have additive inverses, negatives. With multiplication, you just have closure and associativity, and you also have distributive law. A times B plus C is AB plus AC, and B plus C times A is BA plus CA. Okay, now if you have a ring and I is a subset of that, then it's called an ideal. If first of all, it's a subring, that means that it's closed under addition, subtraction, and multiplication. But if there's more to it, in that if you take any element of this subset, I, and multiply it by any element of the ring, you will get, in either way, you will get an element of the ideal. The ideal absorbs elements of the ring when you multiply them by them. That's what an ideal is. Now, what's a maximal ideal? So if you have a ring and if you have a proper ideal, then it's called a maximal ideal if other than M itself, there's no other proper ideals that contain it. So there's no ideal that's strictly between M and R, the ring. The ring is an ideal that contains M, but that doesn't count. That every ideal is inside R. A maximal ideal is one right below that, one that there's no other ones between it and the ring. So let's think about this for example as a second. So for example, one ring could be the integers cross the integers, pairs of integers, and addition and multiplication is component-wise. And this is a commutative ring with identity. It's not an integral domain because it has 0 divisors, but it's a commutative ring with identity. And you could look at elements of the form 6a comma b, and elements of the form 2a comma b, where a and b are integers. Both of these are ideals, and in fact, I is inside j, and that's inside r. Every multiple of 6 is also a multiple of 2, so every element of I is also an element of j, and these are ideals because if you, for example, take something that in the first coordinate has a multiple of 6 and the second coordinate has some integer and multiply it by integer, it still will, in the first coordinate, have a multiple of 6. So it has the ideal properties. Now, I is not a maximal ideal, but J is. To see why J is a maximal ideal, all you have to say is that if you have an ideal that properly contains J, and then what would that mean? That would mean that it has a multiple. It has all the elements of I, which are all the even things in the first coordinate and anything in the second coordinate, and something that's not in J, and that would mean something that in the first coordinate has an odd number, and then using those, you can always get 1, 1 as an element of your ideal, and so that would mean that the ring will have the identity, the ideal will have, J would have identity in it, and any ring that just has identity in it will have to have everything, because every element of the ring times 1, 1 will have to be there, and so it would be equal to R. So there's J is a maximal ideal of this ring, where I is not. Okay, so now what we want to prove, again using the axiom of choice, using Zorn's lemma, is that if you have a non-trivial ring with identity, and if you have a proper ideal of R, then assuming Zorn's lemma, then I is contained in a maximal ideal. So this is a little bit stronger than just saying that every non-trivial ring with identity has a maximal ideal. We're saying that every ideal is contained in a maximal ideal. And the proof is actually very similar to the other one. So take the poset of proper ideals of R that contain I, take those ideals that contain I and are not R. So look at all of those. Those are among which we want to find that maximal ideal. And let's see if we can apply Zorn's lemma, because Zorn's lemma will tell us that there is a maximal element in that poset, and that will be exactly the maximal ideal that will contain I. We order these ideals by inclusion. We'll say that something is less than or equal to something else or related to something else if it's a subset of that. Again, if you take a chain of ideals in P and you look at their union, then that will be an ideal, and it will be an upper bound for the chain of ideals. Now, why will it be an ideal? Because, well, if you take something in J, something in this union, and multiply it by something in the ring, why will it be in J? Well, this guy being in the union was in one of those ideals. That's how it got to be in the union, one of those ideals in the chain. And in that ideal, when you multiply by a ring element, you stay within that ideal, and therefore that product will be in that ideal, and as a result, in the union. And the same thing with addition and subtraction and so forth. All of those properties will hold for the union, because whenever you want to check it, you're looking at just a finite number of elements, and then you can reduce it to one of the ideals in that chain and look at the calculation in that ideal. And in that, because that ideal is an ideal, all those elements will be where you want them to be. And so by Zorn's lemma, by Kuratowski-Zorn's lemma, P will have a maximal ideal. This poset will have a maximal ideal element, and the maximal elements, the elements in that poset are proper ideals that contain I. A maximal one will be a maximal ideal that contains I, and we're done with that proof. Now, trees and spanning trees. So let me remind you what those things are. And so this would be a part of my graph theory combinatorics lectures. If you don't know what graphs are, trees are, and so on, I have videos on those. But briefly, if you have a graph, that means a set of vertices and a set of edges. Edges are pairs of vertices, just tell you which two vertices are adjacent. So if you have such a thing, then a tree is a connected graph that has no cycles. The cycle is when you start from one vertex, go through some edges, and without repeating any vertices or edges, get back to where you started. And connected means that any two vertices, you can find a path from one to the other, starting from one of the vertices, going through edges and vertices, and getting to the other one. So a tree is something that's connected and has no cycles. Now, if you have a connected graph, a spanning tree for G would be a subgraph of G, some of the edges and their vertices, such that it's a tree and it contains all the vertices of G. So it's a tree inside your graph that connects all the vertices. So, for example, here's a graph. It's a finite graph, and here's a spanning tree. So this is a tree. It doesn't have any cycles, and it's connected, but it also contains all the vertices, and so this is a spanning tree for this graph. Now, for finite connected graphs, it's a theorem that one can easily prove that finite connected graphs have spanning trees. So let me do that quickly for you. If G is a finite connected graph, then G has a spanning tree. So what's the proof of that? So you look at all the collection of all subgraphs of G that are connected and contain all the vertices. So if there was a spanning tree, that would be among these, because it contains all the vertices of G. And we're looking at it to be connected. But these guys might not be trees. So we look at all such things. And then S is non-empty because the whole graph is one of the elements in here, but the graph might not be a tree again. And then we took, among the elements of this script S, this collection of all subgraphs of G that are connected and contain all the vertices, among them, we picked the one with the fewest number of edges. And S is a script of S is a finite collection because it's a finite graph. And so we can find T. We can certainly go through and see how many edges each one of those guys have and pick one with the fewest number of elements. And now T is in script S, so in particular it's connected and contains all the vertices of G. And our claim is that this is a spanning tree. Now, why is it a spanning tree? The only thing that could go wrong is that it might not be a tree. But if so, it would have a cycle. But if it had a cycle, we could eliminate one of the edges in one of those cycles and still have an element of S. Because if you're connecting all the vertices and you're connected and you have a cycle, take out one of the edges in that cycle and take it out, you're not going to be disconnecting the two vertices on the other side because they were part of the cycle, so you could go around the other side. And you still have every vertex of the graph. So eliminating one edge would give you another element of S, but T was supposed to be the one with the fewest edges. And so that's a contradiction, which tells us that this will have to be a tree, and therefore we have a spanning tree. But for infinite sets, that you can't make that argument because you just might not be able to, that argument will not work. So for infinite ones, we have G as a connected graph. Then assuming Zorn's lemma, G has a spanning tree. So this is very general. G is a connected graph. It has a spanning tree. Doesn't matter how big it is. So here's the proof sketch. If you have a poset of subgraphs, you make a poset. Whenever you want to use Zorn's lemma, you've got to make a poset, a partially ordered set. You make all subgraphs of G that are trees ordered by inclusion. So you see all the trees in your graph, and you order them by inclusion, meaning that some trees are subsets of other trees. And those are related to those trees. Those are less than or equal to those trees. Now, if T1 is inside T2 in poset, then that means that all the vertices and edges of T1 are also vertices and edges of T2. That's what we mean by inclusion. Now, given a chain of trees in P, now notice that in all of these examples, when I was talking about a chain, I didn't say let T1 be less than or equal to T2 less than, like enumerated the chain, because the chain might be uncountable and I might not be able to index it with the integers. So given a chain of trees in P, the unit of the trees in the chain is also in P. So that's something that you would have to argue with yourself. Again, similar to the previous ones, you always bring it down to whatever argument you want to make, that to one of the smallest trees in the chain. That's where the action is happening, and because of that, we are going to be good. And this is going to be an upper bound for that chain. And by Zorn's lemma, this poset has a maximal element, and that maximal element is going to be a spanning tree for G. Okay, so I'm done with those things, but I want to introduce yet another thing in addition to axiom of choice and Zorn's lemma that's equivalent to them, and that's the well-ordering theorem. So first of all, I'm going to tell you what well-ordering is. So if P is a set, a total order, remember what a total order was a partial order where every two elements are comparable, like a long chain that contains every element. So I mean, a set, you might say, might not have a total order, but this doesn't defend the well order. You have to start with a total order, but not all total orders are well ordered. So total order is a well order if every non-empty subset of P has a least element, that you can find the smallest element for every smallest C. So for example, so now well-ordering principle says that the set of positive integers with less than or equal to is well-ordered. If you take a set of positive integers, and first of all, they're totally ordered, one is less than or equal to each other, and so on, goes up all the way to the top. And then if you take any collection of them, they will have a least number. These are all positive integers, remember, and so you can't just keep going down. At some point, you'll have a least element for some subset. Now, in actuality, the well-ordering principle can be proved from the principle of induction. It's very easy to prove it using induction. On the other, using well-ordering principle, you can prove the principle of mathematical induction. And so each one of those are equivalent. You could take each one of those as one of the axioms that you would like to have in your world. Now, the well-ordering theorem, to not be confused with the well-ordering principle, is actually much stronger statement. It says that every set can be well-ordered. Any set that walks through the door, you should be able to a total order on it, and in a way that it's well ordered. So for example, if you look at the integers, that's not a well order. That's a total order, but it's not a well order, because not every subset of integers, like for example, if you look at all negative numbers, has a least number element. It doesn't. But you can order the integers in a way that it is well ordered. So you could start with 0 as the smallest one, then minus 1, 1, minus 2, 2, minus 3, 3. You can put this order on them. If you put this order on them, then it is a total order, and it is well ordered. Now, if you take any subset, there will be a least element. The well-ordering theorem is actually equivalent to the axiom of choice. You can prove each one of them from the other one. This is all in something called first-order logic. This is actually not true in second-order logic. In second-order logic, well-ordering theorem is actually stronger than axiom of choice. First-order, second-order logic, and so on has something to do with quantifiers and what you are allowed to quantify over. But that's sort of getting us beyond the scope of this lecture, I must say. But the well-ordering theorem doesn't sound right, actually, to be honest, as a theorem, because you might want to think about what would be a well-ordering for the real numbers look like. So that would mean a total order in real numbers. Well, that's possible to do, but a total order in real numbers in a way that if I give you any subset of real numbers, there will be smallest element. How are you going to do that? Okay, so so I want to tell you some of the things that are equivalent to each other. So assuming the Zermelo-Fraenkel axiom, those are the non-controversial sort of basic things that all mathematicians work with and so forth. Assuming those, the following are equivalent statements, meaning that, again, in first order logic, you can prove any one of them from the other ones. One is axiom of choice. We've talked about that, Zorn's lemma, and well-ordering theorem. Those are equivalent to each other, but these are also equivalent to the statement that every vector space has a basis, the statement that every connected graph has a spanning tree, the statement that every ring with identity has a maximal ideal. So any one of these things, if you want them, you need axiom of choice. And if you just take them, you've already taken axiom of choice. From any one of these, you can prove those. There's other ones, like, for example, every poset has a maximal anti-chain. An anti-chain is the opposite of a chain, is a subset of a poset where no two elements are comparable. And a maximal anti-chain is an anti-chain that you can't add any more elements to it. If you add one, every element in your poset is comparable to something and therefore can't be added. The proof that every poset, and again, this is only relevant for really infinite posets, has a maximal anti-chain, that depends on axiom of choice. Or if you can assume this is as your axiom that you like every poset to have a maximal anti-chain, then you have assumed axiom of choice. A mathematician, Jerry Bono, made this joke. Maybe it's due to him, that's who's been contributed to, that if you think about axiom of choice, you'll say that, well, that's obviously should be true. And if you look at the well-ordering theorem, again, by looking at the example of the real numbers, you say, well, that can't possibly be true, that every set can be well-ordered. And who knows about Zorn's lemma? That seems like a weird thing to be able to have an intuition about. And of course, these are all equivalent, so that's why this is a joke. But the point is that our intuition doesn't work the same way for these various versions of the same thing. Now, first, the one question is that, is there any harm in assuming all of these? Now, you could assume the negation of all of them and add that to Zermelo-Fraenkel axioms and get a consistent set of axioms for which you could do mathematics. But the question is that, well, we like the axiom of choice maybe, and is there any reason not to accept all of them? Well, there are things that might give you a pause. So any weird consequences if you accept the axiom of choice? Well, one of them is this thing called the Banach-Tarski Paradox. It says that if you assume axiom of choice, then you can start with a solid three-dimensional sphere, just a sphere, and cut it into a finite number of pieces, and I believe only 5 pieces are needed, and reassemble the pieces. How you reassemble them is just by translating and rotating the pieces. You don't do any stretching or sort of cutting or weird things to them. You don't change their shapes at all. You just translate and rotate them and reassemble them in a way that you get a solid sphere. Again, no holes anywhere, with no holes or empty spaces anywhere, but the volume will be twice the original volume. So in other words, if this is true, which we can prove using axiom of choice, you can start with a little p and keep doing this and get the sum. Now this sounds like a paradox, but it's really what it is that it tells us that our intuition about volume leaves something to be desired. In fact, there are the pieces, the five pieces that you need will not have a clearly defined volume, and so really this is something about our intuition about volume that you need to be careful about, and you need to think about more carefully. But again, this is one of the consequences of axiom of choice, that if you don't like it, then you shouldn't accept the axiom of choice. But if you don't accept the axiom of choice, then not all vector spaces have bases, not all rings have maximal ideals, not all connected graphs have spanning trees, among other things. I have a whole set of videos. This was a part of videos on rings, although we also talked about combinatorics and linear algebra a little bit, and here's some of the other ones in this sequence. There's more to come in the future. Keep hydrated and like my video and subscribe to my channel if you want to be subjected to more videos like this in your feed. See you on the next lecture.